guys, my name is Liad. Welcome back to my data structure series. Today I will discuss a data structure called Sparse table. This is a powerful range query data structure. Today I will discuss about the basic structure of a Sparse table. Let's see a problem first. Given an array of n integers and you are also given q queries. In each query you have to find the maximum element in range from L to R. Okay. N can be in range on to 10 to the power 5 and L and R must be inside on to N. Q is also in the range of 10 to the power 5. Suppose this is the array we are given. We have to find the maximum element between any range L to R. Okay. So suppose L equals 2 and R equals suppose 2, 3, 4, 5, 6. Okay. R equals 6. So in naive approach, what you can do, you can traverse from L to R. In each step, you can update your maximum element by the current element of the array, right? So you will traverse from L. Then firstly, you will update your maximum element by 5, and then you will update your maximum element by the maximum of 12 and your maximum variable, and then you will update your maximum variable by the maximum of 8 and your maximum variable. In this way you will traverse from L to R and you can get the maximum element of this range, right? What is the time complexity of this approach? In each query, in the worst case, you have to traverse the whole array, right? You have to traverse order n time actually. So after q queries, the overall time complexity will order n into q, right? So it is not good. So we have to optimize our time, right? We have to optimize our time complexity. So what we can do to optimize this time complexity? We have seen in the previous video that we also can pre-compute some prefix some data structure. We can do some preprocessing like that, but we know that we can do only prefix sum only on some operation that are invertible, right? But maximum is not invertible, right? You can do something like range sum or range or sum. You can do something like that, but you can't do maximum by this prefix sum data structure. So what we can do then? We will obviously do some pre-computing, but what will be the pre-computing? So we will make some blocks. In that block there will be an answer of some range. Okay. So what will be the block size? Will we make the block size small or big? Suppose if we make the block size small, suppose if we make the block size of 2, from here, from this position, if we make block size of 2, this position we make again block size of 2, then if from this position we'll make the block size 2 from this position also. So in this way we will make all the 2 size block. Okay. Then we can traverse from L to R and we can update our answer. But there is also n by 2 blocks, right? So we have to traverse n by 2 elements. So this is all actually the same. This is not providing much more optimization, right? So we have to, if we do some like the big block size, suppose we are doing something like that, then we are doing something more bigger. If we make big size of block like this, so there will be a small chance that the whole the block size inside a query, right? The query may be inside only this part of block and this part of block can be outside of our query, right? We can't answer the our queries, right? Because we have the maximum element of whole this block, then we have to answer this part of block. So we know all the blocks, we know the maximum of all the blocks, but we from here we can't answer this part of block, right? We can't answer maximum of this part of block. So we can't do this type of operation. So then what will be the approach? So what we'll do is that we will make the block size of power 2. Okay, firstly we will make the block size of 1. From this position we will make the block size of 1. We will make block size of 1 from this position also, from this position, from this, in this way from all positions we will make one size of block. Then we will make two size of blocks also. From this position we will make two size of blocks. From this position also we will make two size of blocks. Then from this position we will make two size of blocks. In this way we will make all the two size of blocks. So to make the block size 2, firstly we will make one size of blocks. So we know that the one size of block, the maximum of one size of block, the elements of that position of the array itself, right? So in from that we can make the one size of block. So then to make the block of size 2, we will use the previous size of blocks that I have already pre-computed. So I will make two size of blocks from this position by uh, from this position where I have made the block size of 1. Then after that we will jump here on size, then the position will be this. Then from here we will take the maximum element of size 1. Then we will combine these two and we will make the maximum of these two. We will store this in the block size of 2 from this position. Okay, then again we will make the block size of 2 from this position. To make this we will combine these two. Okay, from this position we will take the maximum element of on size of on length. Then I will jump of length 1. Then from this position I will take the maximum of length 1. Okay, by combining these two we will get the maximum of length 2, right? Then we will store in this position. Then in this way I will also make the block size of 4 also from every position that I can make. So then I will also use the previous size pre-computation, that is size 2. Okay, so let's make the sparse table. So I have taken the first five elements from the array. Okay, so this is the row and this is the column. The row means the starting position and the column means the length. Okay, so I am giving the index 0 1 2 3. I am not giving the length, I am giving actually the power of 2. So this 0 means the length is 2 to the power 0, that means 1. Okay, so 1 means 2 to the power 1. Okay, in this way. So firstly I will make all the block of size 1. So we know that that the on size block is the element of that position of the array itself, right? So for position 0 it is 3, right? For position 1 it is 5. Then for position 2 it is 12. For position 3 it is 8. For position 4 it is 25, right? Then I will make all the block of size 2 that I can make from any position. Okay, so from position 0 I will make the size of block 2. Okay, so from position to make the blocks of size 2 from position 0, firstly I will use the previous size competition, right? So from position 0, firstly I will take the maximum element of length 1, which is 3. Then I will jump length 1. Next position is 1. So from here I will take the maximum element of size of block size 1. Okay, so it is 5. Then I will combine these two. The maximum of 3 and 5 is 5. Then I will store this in the block size of 2 from this position. Okay, so it is 5. Then from this position I will make the block of size 2. So for that I will use the pre-computation in the same way. I will take the maximum element of block size 1. From this position is 5. Then I will jump 1 length. then the next position is 2, then I will take the maximum element from this position of length of block size 1. This is 12, so I will combine this 5 and 12, then the maximum will be 12. I will store this in the length of block size 2 in from this position. Okay, in this way I will make from this position, so this position will be maximum of 12 and 8, so it is 12, and from this position it will be 8 and 25, so it is 25, right? So from this position I can't make block size of 2, right, because this is the last position, so there is no size of block 2 from this position. Okay, so then I will make all the blocks of size 4 from each position I can make. Okay, so from position 0, firstly I will make from position 0. To do this I will use the previous size pre-computation, which is 2. So from this position I will take the maximum element of size 2, that is 5, and then I will jump up length 2, so the next position will be 2. Then from this position I will take the maximum element of length 2, which is 12, so maximum of 5 and 12 is 12, right? So then I will store this in the block size of 4 of from this position. Okay, then I will make from this position also, so for that I will use the previous specific competition. So I will take the maximum element of block size 2 from this position, it is 12, then I will jump of length 2, so then the next position will be 3, then I will take the maximum element of size 2 from this position, so it is 25, so maximum of 12 and 25 is 25, right? Then I will store this inside the block size of 4 from this position. Okay, then I will also make the block size of 4 from this position, but you can see that it is position 0 1 2, that means this position. So from this position there is no block of size 4, right? I can't make from this position a block size 4, so I can't make any of block size for from any other position, right? If I can't make from this position, then I can't also make from this position and also from this position, right? So then I will make the block size of 8, but there the length of the array is only 5, so I can't make any block of size 8, right? So I will not go further then. So this is all the sparse table I can make from this array. Okay, let's see the implementation. So this is the log variable I have taken. I will initialize this. The log variable is what is doing log variable is that it is storing the maximum power of base 2 of any length we can make. Okay, suppose firstly I have initialized the 1, log of 1 equals 0, because 2 to the power 0 is 1, right? We can make the maximum power 0 of base 2 to make the length 1, right? Then I will make all the size of any other length from 2 to max n that I have. So it can be 2 to the power 10 to the power 5 in this problem. Okay, so to make this I can have two types of integer. One is power of 2 itself, so suppose 4 it is power of 2, then I can have not power of 2 an integer, so suppose this is 5, right? So to make the maximum power of base 2 of any power 2, we can make this easily, right? Because we can go to the previous power, that by dividing by 2, then what I have already initialized to this power, so the maximum power of base 2 to make this length is 1, right? So then I will add 1 to this, and then I will store this result into this integer, right? So this is simple. So then if the integer is not power of 2, then what I will do, so if you observe this carefully, then you will notice that I can make all the integer actually the same of this until I get another power of 2, right? So if we get the next power of 2 is 8, right? So between these 4 and 8, which is 4 5 6 7, all the length have the maximum power of base 2 is 2, right? So this is actually same. Then what I will do is, to do this, I will make all this length to divide by 2, rounded down. Okay, I will divide this by 2, rounded down. Then this will be, all this length will be 2, right? Then I will add 1 to this and store this into this integer. Okay, in this way I will make log variable. Then I have initialized k equals to log max n. So that is the maximum n I can have, maximum power of base 2, and that I can make to make the length of max n. Why I need this? Because I will make a sparse table of length max n, which is the starting position, and the maximum power of base 2 that I can make. So it is k, right? The maximum length will be n, so then the maximum power of base 2 we can make is k. So I will make array k plus 1 of size k plus 1. Okay, then we know that the block of size 1, which is 2 to the power 0, the element of the array of that position itself, right? So I am initializing this in this loop. Then I will make all other size of block. Okay, so for that I am traversing from 1, which is 2 to the power 1, till k. Okay, so I don't need beyond k. Okay, then I will make all the blocks one by one. Firstly I will make a block size 2, then I will make block of size 4, then I will make block of size 8, till I can make what size of block. So firstly I am traversing the array. Each step what I am doing is that from this position I have to make length of block size to the power j, right? So for that I am using the previous SP computation, which is from this position I am taking the maximum of length to the power j minus 1, which is the previous size. Then I am jumping to the power j minus 1 length from this position, which will be I plus on left shift j minus 1, right? If you don't know about the left shift operator, check out my bit manipulation playlist. I have a video of bitwise operators inside that. So I have discussed all the bitwise operators and their operations in that video. Here on left shift j minus 1 is 2 to the power j minus 1. Okay, so I plus 2 to the power j minus 1 means from I am jumping 2 to the power j minus 1 length. Okay, then from this position I will take the previous length also, which is 2 to the power j minus 1, right? Then I am combining these two. I am combining these two maximum by maximizing this. Then I am storing this in this position. Okay, so I am doing in this way. I am building the sparse table in this way. So what about the time complexity then? I am firstly traversing whole the array, which is n, length n in this case, and in this loop firstly I am traversing from 1 to k, which is the maximum power of base 2 we can make to make the length n. So you know that is actually the binary representation of any number. The length of binary representation of any number is actually log n, right? So it is traversing log n length, and here I am traversing n length, right? So overall complexity will be n log n. To build a sparse table we need n log n time complexity. So this was all for today. In the next video we will see how can we answer a query by using a sparse table. So till then keep practicing, and thank you for watching.